Objectives of this section. So what we expect from you, ya shabab, after finishing this section. Inshallah, after finishing this section, you will be able to identify what does the first derivative says about the function itself. And you will be able, inshallah, also to use the first derivative test to find the local maxima and local minima. Also, you will be able to identify what does the second derivative says about the function. So it will tell you where the function concave up or concave down. And finally, we will study, inshallah, the inflection points and the second derivative test. But at the beginning, let me remind you, Shabab, about the relationship between the graph of the function and the graph of the function. I think you know from chapter 2, if you have the graph of the function, do you remember that? Let's say this is the graph of the function. This is the graph of the function. You can sketch the graph of the derivative. You remember that? How to sketch the graph of the derivative from the graph of the function, Shabab? When the function is increasing, so this means that the derivative is what?
Positive, above the x-axis.
Positive. So it means that it will be above the x-axis. So it could be, when it is 0, when the derivative is 0, you will have x-intercept here and here. You will have x-intercept for the function. After that, it will be above the x-axis. It will be here below the x-axis when it is decreasing from here to here. And after that, it will come positive again. So it could be like this, whatever. So this is the graph of the derivative. Now we will use the derivative to sketch the function. So we will get some information from the first derivative to sketch the graph of the original function. And the idea is the same as you notice there. So let me start with the ID test. What is the ID test? It is shortcut for increasing, decreasing test. And this will answer the question, what does f prime says about f? You remember, Shabab, when the function is increasing, where it is decreasing? If you have x1 less than x2, if the value of the function at x1 is still less than if the value of the function at x2, then the function is increasing. So it will go in the same direction. If x increase, y increase. But if the opposite is happening, if the value of the function at x1, it becomes to be greater than, so it means that if x is increasing, y is decreasing. It gets smaller and smaller because the smaller value, at the smaller value, it is greater. So in that case, we will say that this is what? Decreasing. This is increasing. This is decreasing. Is that clear? But of course, ya Shabab, it is not easy to check this. You need to check this inequality. Every time you need to check if it is increasing or decreasing. But there is an easy test for that. This test says what? If the derivative, the first derivative, is positive on an interval, then the function itself, it is increasing on that interval. And this, you remember, if you remember what I told you here, when the function is increasing, the derivative is positive. So when the derivative is positive, then the function is increasing. And when the derivative is negative, the function is decreasing. And the proof of this test or theorem, indeed, it is in your book, and it depends on the main value theorem. If you remember the main value theorem, if you have f of b minus f of a equals to f prime of c times b minus a. Let's take in our case, in this case, let's take x1 and x2. So this will be x2, and this is x1. This is x2 and x1. Here, see, it is any number between x1 and x2. Now, this is positive, Shabab, because why this is positive? Because x1 is less than x2. So this is positive. So now, now we have two cases. If this is positive, this will be greater than what? This will be positive. If this is negative, this will be negative. So now if this is positive, this means that f of x1 will be what? This will be greater than 0. This will be less than 0. If this is greater than 0, this means that f of x2, let me write, you will have this case. In that case, you will have this case. If f of x1 minus f of x2, or the opposite, f of x2 minus f of x1 is greater than 0, move this to the other side. You will have f of x2 greater than f of x1, which is this case, f of x2, it is greater than f of x1. And in that case, the opposite one. This is the proof, by the way. We have proved that one. If this is positive, then it will be increasing. If it is negative, it will be decreasing. If you are interested in the proof, Shabab, it is very easy. It is in your book, included in your book. I think it was better to include it here, but it's okay. Now let's take an example. It is better to now apply this test for this function. Imagine, Shabab, that you need to find where this function is increasing, where it is decreasing without this test. Is it easy?
No.
Can you know where it is increasing, where it is decreasing? It is not easy at all. You have a function now of degree 4, of degree number 4. To find the intervals on which this function is increasing or decreasing, you need to find the first derivative and to apply the increasing decreasing test. So now this is the first derivative. It is a polynomial, so easy. Now you need to factor this because you need now to know where it is greater than 0, where it is less than 0. To know where it is greater than 0, where it is less than 0, you need to know first where it is 0. So you will put it equals to 0. So you need to solve this equation. You need to factor it. So he take 12 as a common factor, 12x as a common factor. So we left up with what? X squared minus x minus 2. Factor this trinomial. Factoring this trinomial will give you these two factors. Now you need to put this equals to 0. So in this case, what you will have? What are the zeros of this function? 0
and 2 and
minus 1
and negative 1. So these are the zeros. Now we need to know, ya Shabab, where it is positive, where it is negative. To use the increasing decreasing test, we have to know where it is positive, where it is negative. What do you suggest? What to do?
Draw a table.
We need to draw a table. So we know now by the way, these are critical numbers. Do you know that? 0, 2, and negative 1, they are critical numbers because the derivative at them is equals to 0. So now what we will do, we will make a table of values. Let me draw the table of values where, let me here start drawing the table of values. So it is, did he give me closed interval or he didn't mention any interval? So in general, from negative infinity to infinity. So my critical numbers are what? 0, 2, and negative 1. So this is negative 1, the smaller one, then 0, then 2. Now this line, Shabab, will represent what? Will represent the first derivative. Okay. Now what are my factors? My factors are x minus 2, x plus 1. These are the three factors that I have. Now for x, what is the 0 of x, ya Shabab? It is 0 here. Am I right?
Yes.
So after that, لاحظ معي إن كل الإكس يا شباب هنا positive. And after 0, it will be positive. Before that, it will be negative. Now look at x minus 2. X minus 2, where it is 0? It is 0 here. After that, it will be positive. Before that, it will be negative. Now x plus 1, it is 0 here. Before that, I think we make it a little bit. This is x minus 2, this is x plus 1. Now it will be negative. After that, it will be positive. Now the derivative is this one, the product of them. So the product of this times this times this, what we will have? Negative times negative times negative, it is what? Negative. Here it will be positive. Negative times negative, positive. Here it will be negative because positive times negative is negative. Here all of them are positive. Now where the function is positive, let's hear from negative infinity. By the way, let me just write this here. This is negative infinity, ya shabab, and this is infinity. Now the first derivative, let me here do it here. The first derivative here. This is the first derivative. The graph here. Let me do it here. This is the first derivative. So who is positive, who is negative here? The first derivative. Now let's talk about the function itself. The function itself. Now the function here, is it increasing or decreasing? When the derivative is negative. According to the test, if the derivative is negative, the function is what?
Decreasing.
And if the derivative is positive,
Increasing.
the function itself is increasing. So this means that the function here is decreasing. So we will do it like this. This means decreasing. And here it is what? Increasing between -1 and 0. So from negative infinity to -1, it is decreasing. From -1 to 0, it is increasing. From 0 to 2, decreasing. From 2 to infinity, increasing. Is it clear, ya shabab? So it is just make a table of values and you will be able to know where it is positive, where it is negative. I advise you to use this table, ya shabab, instead of this table that is included in your book. Your book is using this table. I don't like it indeed, but unfortunately I didn't have time to change it and to modify it. But it's okay. I think you get my idea. The idea is, first of all, to write intervals. This is what I mentioned, from negative infinity to -1. Here it is. Between -1 and 0, between 0 and 2, x greater than 2. And check the factors, the signs of the factors, then multiply them. Negative times negative is negative, and so on. Maybe some of you, they like this one. Now here, the function is decreasing. Here it is increasing. Here decreasing. Here increasing. But I advise you, as I said, to use this one. And of course, it will be after that easy for you to decide. And I think there is a missing here. We should mention here what it is mentioned already. Okay, now we will go back to 4.1, the local maximum and the local minimum values. So we have here what is called the first derivative test. The question is, what is it about? The first derivative test is about the local extreme values. It is about the local minima and the local maxima. Suppose that C is a critical number. So first of all, we have C is a critical number. What does that mean? That it is the derivative at it is 0 or does not exist. This is the meaning of critical number. F is continuous. So we have F is continuous function. So F is continuous, C is a critical number. Then, if the first derivative changes from positive to negative at C, then F has a local maximum at C. Again, if it changes from positive to negative, the first derivative, then it is a local maximum. If the first derivative changes from negative to positive, then F has a local minima at that point. And this should be clear, shabab. If the function is the first derivative is positive, لما تكون الفirst derivative يا شباب positive, this means increasing, ولا لا? And the function itself will be increasing. And if it is negative, it will be decreasing. So here, the first derivative, the slope, if you remember the slope, here it is positive, here it is negative. If this happens, ya shabab, in between here, we will have what? At C, this is C. So this is the value of the function at C. Now, at C, the function here is changed from positive to negative. So at C, we will have what? We will have local what? Local maximum. If it changed, if the function changed, it was decreasing, it was negative, the first derivative is negative, and then it becomes positive. Then at this point, what we will have? We will have local minimum. Here we will have local maximum.
What about the x-cube function?
Yes, this is a good question. Does it change or not? Let's see now if the derivative positive to the left and to the right. So the derivative, it is positive from the left and from the right. And also here it is negative to the left, negative to the right? Then there is a positive on both or negative on both. Then f has no local maximum or minimum, like this, for example, here at this point, ya shabab. Is there any change? The function here, the derivative is negative. Here it is negative. So after it and before it, it is negative. Then there is no maximum or minimum, local maximum or local minimum at that point. Now, do you remember, ya shabab, who asked about the x cubed function, ya shabab?
Me.
Nawaf?
Yes.
Yes. First of all, is this function is positive? Sorry, continuous? It is continuous. It has zero, at zero, it has a critical number. The derivative at zero is zero. Is that right?
Yes.
But the derivative here change from positive to negative or
No.
not?
No.
Look at x cubed. This is x cubed, f of x. Take the derivative. What is it? 3x squared.
3x squared.
Always what?
Positive.
Always positive. So it is the third case. If it is positive to the left, positive to the right, it will be always positive. So there is no local maximum or minimum at that point.
Yes.
Excellent. Thank you for this question. Let's go back, ya shabab. Let me explain it here. I think it is better than my sketch here. Look here. Oh, I put it for you because here the function, the derivative here is positive, ya shabab, increasing, and here it is decreasing. So at C, before C, it was negative, the first derivative, and after that it is positive, or the opposite here. Then it is local maximum. Here it is local minimum. Here it is not. Here it is not, because there is no change. It's still always, the derivative is always positive, like the case, of course, of increase x cubed. Also in case of x cubed, you know what? The function is keeping increasing, so the derivative is always positive. Now, let's go back, ya shabab, to our example. Can we know now? Can you tell me, ya shabab? طبعا I have here 3 points اللي هم 0 و 2 و negative 1. At them they are critical numbers. At them the derivative is 0. So the derivative is 0 at 0 and at 2 and at negative 1. What do you think at negative 1? What do we have? Local maximum or minimum?
Local minimum.
At
negative 1, local minimum.
Minimum.
Sure?
It's from negative to positive.
It is a change from negative to positive. The first derivative change from negative to positive. Look, when you have something like this, down and then after that up, what will you have here?
Local minimum.
Like
Minimum.
Minimum. So here we have local minimum. Yeah, shabab, if we can agree in short to write it m small. So if I write m small, I mean local minimum. Here it will be what? M capital. You can write it as local maximum. It is here, it is doing like this. So here, of course, you will have local maximum. Here, it will be what? It is doing like this. So derivative is changing from negative to positive. So here we will have
Minimum.
Local minimum. Why we said local, shabab? We cannot here check because I don't have interval. It might be, by the way, it might be absolute. How to check that, shabab? This is a good question. One of your colleagues in the previous section asked about this. What about absolute or the global maximum here? Can I find them?
We can substitute and find the greatest and the lowest.
Yes, like we did in 4.1.
How to guarantee that they are the absolute or maximum or minimum, or there is no? Now, this one, you need, in fact, to consider the whole graph, the whole function. If you remember, ya shabab, this is the function. This is a polynomial. Do you remember the end behavior of this polynomial? Because it is of degree that is even, and the leading coefficient is positive, so it will be up to the right, up to the left. Do you remember that?
Yes.
Yes.
What do you think? It has absolute maximum?
No, only
It
minimum.
doesn't have absolute maximum. Impossible. Unless we have a closed interval, unless we are studying this function on a closed interval, not on the whole domain. from negative infinity to infinity. But for sure, ya shabab, because it is even power, even degree, even with even degree polynomial, it has a local minimum, absolute minimum. Why? Remember x cubed?
Yes.
It should have any polynomial, whatever there will be absolute minimum, and you can find it. It will be at 2 or at what? We have two local minimum. These are nominated to be local, to be absolute. So it could be at -1 at or 2. Now we will see that when you need to find the value of the function. What is the value of the function at -1? What is the value of the function at 2? And what is the value of the function at 0? Now يا شباب لو كان الكوفيشنت هذا لو كان leading coefficient negative, it will be the opposite. It will be like this. Not necessarily here. Could be here anything. Do anything, but at the end eventually it will be like that. So in our case, I think we have the value of the function. This is what I did, Shabab. We did before this example one. This is example about the same one. And we have noticed that we have the function has a local minimum at -1 and at 2. You need to find, ya Shabab, what is this? It has a local minimum at -1, but what is the local minimum value? The local minimum value is the value of the function at here. You will substitute in the function. It will be f at -1 and accidentally f at -1 is 0, as the same as the function itself, as the derivative also. And at 0, it has the local maximum. What is the maximum value? The maximum value here, the local maximum value, it is 5. It is f at 0. F at 2, it is -27, and it is the local minimum. And if you compare, Shabab, this, we said for this one we have absolute
Minimum.
maximum at, it could be absolute minimum, not maximum. It has absolute minimum at, it could be at -1 or what?
Or 2.
Or 2. What do you think?
2.
2. Yes, 2, because
Its lowest point will be -27 if you sketch the graph of this function. But ya Shabab, since he is asking about the local, don't bother yourself, but it is okay to have this in mind. So I think, ya Shabab, it is just about this table. To summarize, if you did this table in the right way, you can also know where it is increasing, where it is decreasing, where is the local maximum, where is the local minimum, and you need just at the end to find the values at these points. If he asking about the values, the maximum value and the minimum value. But if he just asking about the x coordinates, where it is at what it has minimum or maximum, you can just stop there. Another example, find the local maximum and minimum values. So we need to find f at what is the maximum value, f at what is the local minimum or maximum. And good, look here, he gave me a closed interval. So I can apply the closed interval method. I can know now exactly the absolute if I want. Because what I will do, I will find the critical numbers and I will evaluate at the end points also to check the absolute maximum or minimum, the global. Now, what to do, ya Shabab, to find the local maximum and the minimum values? We need to start with what?
Derivative.
The first derivative. So the first derivative is what? 1 plus 2 cosine x. So we should start by finding the critical numbers, and to find the critical numbers, you need to find the first derivative. So now what we will do? We will put this equals to 0, and if you put this equals to 0, what is the equation that you are going to have? It will be cosine x equals -½ What is x, ya Shabab? Cosine x is negative. Cosine x is negative. So in which quadrant we are? We are in the second,
2 and 3.
Third.
and third. So what is the function that you need to ask yourself? What is the function that its cosine is ½ before asking yourself what is the function that its cosine is -½
Pi over 3.
It is pi over 3. But in the second quadrant, it is 2 pi
2
over 3.
pi over 3.
And here, 4 pi
4
over
pi over 3.
You need to recall, ya Shabab, how to solve trigonometric equations. So according to that, x is 2 pi over 3 or 4 pi over 3. Now these are the critical numbers. Now what we will do, ya shabab, we will make a table, the numbers line, but we will not do it now for infinity and negative infinity. Why? Because I have closed interval here. So I will just do it from 0 to 2 pi. Now let's say that this is 2 pi over 3. This is 4 pi over 3. Now we need to determine the sign of, we don't have factors here, so it is easy. Let me put it here. This is the first derivative. Now the first derivative here, is it positive or negative between 0 and 2 pi over 3? Let's recall the quadrants. This is 0, this is pi over 2, this is pi, this is 3 pi over 2, this is 2 pi again. So 2 pi over 3, it is in the second, it is here. This is 2 pi over 3. 4 pi over 3, where it is? It is here. 4 pi over 3, it is in the third quadrant. Okay? Now I need a number between 0 and 2 pi over 3. Which one is better to choose, ya shabab, to know if it is positive or negative? choose باي اوفر 2. خذ مثلا باي اوفر 2. تعال للديريفاتيف. هذه هي الديريفاتيف. Both instead of x by over 2, what you will have? Cosine by over 2 is what?
0.
0. 0 times 2 is 0. 0 plus 1 is 1. 1 is positive. So it is positive. Now, between 2 pi over 3 and 4 pi over 3, which number is better to choose?
Pi.
Pi.
What x equals to pi? Cosine pi?
Minus 1.
Negative 1. Negative 1 times 2, negative 2. Negative 2 plus 1, negative 1. So it is negative. Now, between 4 pi over 3 and 2 pi, between this one and this one, it is better to choose 3 pi over 2. Choose 3 pi over 2. This will be 0 again, because cosine 3 pi over 2 is also 0. So it will be positive again. Now, here, the function itself, the function will be increasing or decreasing in this interval?
Increasing.
Increase.
In this interval, it will be?
Decreasing.
Decreasing. So you can also make here, you can say here I, which means increasing, or D, which means decreasing. It is up to you. But I prefer to use these rows to include to mention that it is increasing or decreasing. Now you can now decide, Shabab, is this here? We have what? Maximum or minimum?
Maximum.
Minimum.
Maximum.
Local.
Maximum, yes.
Negative.
I'm talking about local. So here we have local.
Maximum.
Maximum.
Maximum. Because it is doing like this, increasing and then decreasing. Positive, then negative. And if it changes from negative to positive, it will be local.
Minimum.
Minimum. If you want to find the absolute maximum or the absolute minimum, what you need to do more? You need to find the value of the function at 2 pi and the value of the function at 0. And then compare. So you need now, Shabab, to find the value of the function at 2 pi over 3, because he asked about the local and maximum values, and then you need to find the value of the function at 4 pi over 3. The value that you will have here, it will be the local maximum, the local minimum. And you can compare it with the value of the function at 0 and 2 pi. By the way, the value of the function at 0, it will be what? 0. Am I right? Then sine is 0, 0, and this is 0. So f or g, it is g indeed. I'm talking about f here. So why you didn't correct me? This is wrong. This is g. It is not f. It is g. So here it is g also. So here g at 0. G at 0 is 0, Shabab. And g at what? At 2 pi, it is what? 2 pi. Am I right?
Yes.
Yes. Let's see now what will happen. He make a table of values by the same way. And what was the value of the function at 2 pi over 3? 3.8, something like that. Here it is. And this is the value of the function at 4 pi over 3. This is the local minima. And you know what is 2 pi, Shabab? Do you remember 2 pi is almost what?
6 point something.
6 point something. So it looks like it has absolute maximum there. It has absolute maximum at 2 pi. And it has absolute minimum at 0. And of course, it has local maximum at 2 pi over 3 and local minimum at 4 pi over 3. Is that clear, Shabab? Any question about this before going to the next part? This part is about the concavity. The graph of a function here is given. Here, this function, Shabab, if we are talking about concave, if you know what we mean by concave up and concave down, when a function have behavior like this, this is concave up. And when it is doing something like this, not necessarily by the same way, it could be like this only. This is concave down. Okay? Formally, how to define that? If a graph of a function lies above all of its tangents on specific interval, then it concaves upward. Look here on this graph, this one. This concave up or down, Shabab?
Up.
It concave up. If you draw any tangent for this graph, it will be below. The graph is lying above. The graph is lying above its tangents. But when the graph lies below its tangents, it will be concave down. So this is concave up, this is concave down. It is not easy to check all the tangents, are they above or below? So what we have a very interesting test for that. The concavity test that is depend on the second derivative. Now, let's look at this graph. This graph from here to up to here, it's concave what? It is CD. For short, we will say concave down, and it's CD. And it starts to change from concaving down to concave up at what? At the point P, here, the point B. After that, it concave down, up, sorry. Here it is up on this interval. Until C, until the point C. After C, it starts concave down. Then at D, it concaves up. It concaves, by the way, still concave up, ya Shabab. It doesn't change at E. At the point E, there is no change. At B, there is a change. It was here concaving up to here. But after that, at this point, it start doing that down. Now, we will answer now the question that says, what does the second derivative says about the original function? And this is what is called the concavity test. If the second derivative is positive over a specific interval, then the graph is concave up, the graph of the function itself, concave up on that interval. And if the second derivative is negative over specific interval, then the graph of this function concaving down over that interval. And I think it is clear. What do you think, ya Shabab, here? The derivative here, the second derivative, is it positive or negative?
Negative.
The second derivative from A to B over this interval.
Negative.
It concaves down, concave down. So it is negative. Here, over this interval from here to here. Positive. It concaves down, it concaves up. So the second derivative is what?
Positive.
Positive. And so on. Now, this is an interesting example for as an application, this is from I think biology application about these ideas. Here, this figure is showing a number of P's. He is asking about how does the rate of population change and where it is maximum and where it is concave up and down. So let's see, what does this graph tells us, Shabab, about the population of these P's? Now, if you look at the graph, and this is P, the population, the graph, this is the function itself. Now, if you look at the number of P's, let's say this is what? This is time in weeks. And this is the number of P's in thousands. So now, if you look at the first 3 weeks, the number of the bees is very small. It starts initially very small, and also the rate of change, yani the rate of increasing. The rate of increasing means the first derivative. So what we can see from the graph, the graph, that the slope of the curve, which means what? Derivative. Increase. Of course, it is increasing. Number of the bees is increasing. We see that the rate of increase, now we are talking about the first derivative of the population, is initially very small. It starts very small. The slope here, the slope is very small. So there is no big change here. And until it reach its maximum value, the maximum here value for the slope, it is 12 at 12. After 12 months, like here 12 months, it start. I think the slope, Shabab, if you think about the slope here is small. Start now being bigger and bigger and bigger, and until it has the maximum value at 12. Here the maximum, I think the slope is the largest. After that, the slope starts slowing down. It will be now smaller and smaller until it becomes zero. Like here we have a horizontal tangent. So here the derivative is almost zero. So the rate of change, they stop change, no more increasing here in the number of bees. And it decreases as the population begins to level off. Now, as the population approaches its maximum value, the maximum value of the population is almost at this point. He said that it is almost 75,000. The rate of change is start approaching zero. What does that mean? No more increasing. So the rate of increasing of the number of the bees is very slow. No more change. And of course, you can see, Shabab, that the curve appears to concave up until 12, the week number 12. After that, it starts concave down. So here, it was like this. Now it starts like this. What we will call this point, at 12, like at 12, we have 38,000, the number. This point, it is very important point. It is, they call it the inflection point. Why? Because why it is important? Because the curve change from concave up to concave down at this point. And in general, this point can be defined as follows. A point P on a curve is called inflection point if what? Number one, if is continuous at P at this point, and the curve, condition number two, the curve change from concave upward to concave downward, or from concave downward to concave upward. Then it is called inflection points. So first of all, to have inflection point, you should consider where the function change its concavity. Look at this point, if you remember. Who can tell me what are now the inflection points? This point P, B, and C, and D, and P. These are inflection points. Because the function, Shabab, if you look, it was concave down. Until this point, it changed, concave up. Be careful, Shabab. Some of you, they may ask, why it is not this point? Is this point of inflection, Shabab? Here. Is this point of inflection point? The graph here is concave down, and it's still concave down. So it is still, Shabab, it is not. The inflection point, it is the point at which the graph will change from concaving down. So if you have a graph like this, the inflection point here will be in the middle here. Here it concaves down, and here it concaves up. Why this point is not? Why this point is not inflection point?
It's up.
It didn't change
after the point.
It doesn't change. It's still concave up, and it continues also concaving up. It is not here. If it was like this, it starts like this, we can say that if it was like that, and I don't think it cannot do that at this point. So here we have only B, C, D, and P are the points of inflection. Now let's apply these ideas to sketch the graph of the following function. Sketch a possible graph. And we could have several graphs, but this is just, we will choose one of them. Now we need to summarize the information that we will have. Now he said the derivative of this function is positive on that interval from -1 to, let me start here drawing the graph. This is negative, this is 1. From -infinity to 1, the graph is what?
Increasing.
Increasing. So here it is increasing. So it will do something like this, Shabab, here. It will not change. It will not be never ever decreasing. Now the derivative is negative from 1 to infinity. Now here it will be decreasing. Here it will be something like that. Okay. So here it is increasing. Here it is decreasing. Let me write here. This is increasing here, decreasing here. So to summarize. Now the second derivative is positive on this interval from -infinity to -2 and from 2 to infinity. Then it is negative between -2 and 2. So we have to add 2 points here. Let me add here -2 and here 2. Now what you can say about -2 and 2 يا شباب؟ لاحظ معي انه الفانكشن change from positive to negative. The second derivative change from negative to positive, from positive to negative. At what? At -2 and 2. So at 2 and -2 we have what? We have inflection
point.
Inflection. So keep this in mind. I don't know where to put it, here or here, whatever. Keep in mind that at -2 it will change from concave, from -infinity to -1. It concaves what? Here.
Up.
Here it will concave up. Here CD, concave down. Keep this in mind. We'll do something here between something like this. Something like this. This is just initially, but we cannot decide now. We need to finish the information. Now look here. This is the important part. The limit of the function when x goes to negative, x goes to positive or negative infinity of a function equals to a specific number. What is this number? Represent what?
Horizontal asymptote.
Y equals L is a horizontal asymptote. Thank you very much. Yes, you're right. This means that this line here to -2 is a horizontal from the left. So let me draw it here. This is the horizontal tangent. Y equals to -2. So it means when x goes to -infinity, here it doesn't matter. It could be like this, but initially when x goes to -infinity, approach the graph like this. Okay. So what we know until now, it is doing like this or like this. I don't know, but like that. Now also we have here the limit of the function when x goes to infinity. When x goes to infinity, it is 0. So this means that the graph will do this. Eventually at infinity, it will approach the x-axis. Y equals 0 is the x-axis. So now we can start doing like this. Now let's combine these informations, Shabab. Now it will do. Now let's say it because it starts here, and let's do like that. We can do it like this, Shabab. We will see. Now it will concave up. It keep increasing here, so it will increase until 1. So at 1, what we have, Shabab? At 1, what we have, by the
maximum.
way? We have a maximum. Let's say this maximum is here, like that. So here it will have something like this. So I can now start thinking about my function. So I think it will cave now. It will concave what? It will do something like this. At 2, after 2, it will concave up. Let's see. I will check that later, Shabab. Now from -infinity to -2. Concaving up. This is concaving up. 2, it has what at -2? So it will change now from concaving up to concaving what? Minimize my, or let me do it more, no problem, like this. But it will not be maximum. I want my maximum to be here. Let me do my maximum like this, like this. Let me check if it will be okay. Now let me check my information, ya shabab. Oh, I don't like this. I need to have it something like this, very smooth. It should be smooth curve. And again, it is not maximum. So we need to I think it is better to lower it, to make it like this. Yes, I will see if it is changed or not. And I need to check my information, ya shabab. What do you think? Now let me check. Is the function increasing from negative infinity to 1? Is it increasing?
Yes.
Is it decreasing from 1 to infinity? Yes.
Yes.
Is it concaving up from negative infinity to negative 2? This is concaving
Yes.
up. Then it concaves down from negative 2 to 2. Yes, it is. If you check that. And from negative 2 to 2, it is concaving down. Also from 2 to infinity, it should concave up. So let me do it like this. It should do something like this. Concaving up, not down. Excellent. Now, of course, for this is horizontal, this is horizontal. When x goes to infinity, it is approaching 0. When x goes to negative infinity, it approaches negative 2. And that's it. This is one possible graph. You may have another, but you need, ya shabab, always, when you finish your graphing, check the given data, the given information. Are they satisfied or not? Any question, ya shabab? Let's go now to the second derivative test, a very important test, ya shabab. But of course, it is not necessary. In many situations, you don't need it because the first derivative test will be enough, as we will see, inshallah, next class. Suppose that if double prime, if the second derivative is continuous near a point, if the derivative, the first derivative at that number is 0 and the second derivative is positive, then f has a local minimum. So this is another test for the local minimum and local maximum values. If the first derivative is 0 and the second derivative is negative, then it is local maximum. Look how to apply this. Let's take an example. This is a function. You need now to study everything about this function. But let's focus on this. What you need to do to apply this test, ya shabab? You need the first derivative. طبعا the function is continuous. Find the first derivative. This is step number 1.
Equals 0.
Then the second derivative, you need the second derivative. Find the first derivative and then the second derivative. Now here you need to factor it because you will put it equals to 0. Put it equals to 0 to find what? To find the critical numbers. Because we need f prime at c equals to 0. So if it will be f prime at 0 and f prime at 3 will be 0. Now what you need to do, you need to find the second derivative at 0, the value of the second derivative at 0. Is it positive or negative? Come here. What do you think? At 0, it will be what? It will be 0. Because we have x here. Now, so we cannot conclude anything here. This test does not tell me anything about the second derivative at 0. Now, the second derivative at 3. What do you think? Is it positive or negative?
Positive.
This will be positive. It is positive. So here at 3, what we have, shabab?
Decreasing.
We have
Local minimum.
Local minimum.
local minimum. So here at f at 3 substitute by 3 here is local minimum. So we applied now the second derivative test to find that. But indeed, ya shabab, it wasn't necessary, by the way. We can do that only by the first derivative. Do you remember? You will see where it is starting increasing and then when it is decreasing by applying the first second derivative test. We will continue inshallah that next class. Don't forget, ya shabab, that next class we have a quiz as we have agreed last week. Inshallah, our quiz will be next class, and it will be a short one, quiz number 11, about sections 3.9, 3.10, and 3.11. It could be 2 to 3 questions at most. See you, inshallah, shabab, next class. And if you have any question, before I leave?
Dr.